Right now, in the empty space in front of your face, there is enough hidden energy to boil every ocean on Earth in a single instant. That is what our best theory of reality predicts. Empty space should be roaring, violent, impossibly heavy. Yet when we measure the real universe, almost none of that energy is there. The prediction misses by a 1 followed by 120 zeros, the largest error in the history of science. Ahead lies the force ripping galaxies apart, a bubble that could rewrite matter itself, and the deepest crack in all of physics. If this thrills you, a quick like or subscribe truly helps this channel grow. Now, let us begin. Picture a sealed steel box, floating in the darkest gap between two galaxies. Reach inside and take everything out. Every speck of dust, every stray atom, every wandering particle of light. Pump out the last breath of air until the box holds less than the space between stars. You have built the emptiest thing that can exist. A perfect vacuum. Nothing left at all. That is the story we tell children. It is also completely wrong. For most of history, empty meant empty. The ancient Greeks argued about it. Some said the void was pure nothing, a stage with no actors. Others could not stand the idea and insisted the world was packed solid with invisible stuff. For 2,000 years, empty space stayed a background, a container, the place where things happened, and nothing more. Then physics looked closer, and the background started to move. Here is the first crack in the old idea. When scientists learned to cool matter down, they found that atoms slow as they lose heat, chill something enough, and its particles crawl. Common sense says that if you keep cooling, you reach a point where everything freezes into perfect stillness. Absolute zero, the coldest cold. The moment all motion stops, yet motion never fully stops. Even at absolute zero, even when every last scrap of heat is gone, the tiniest pieces of the world keep trembling, a faint, permanent shiver that no amount of cooling can silence. That shiver should not be there, and it was the first hint that the emptiness inside our steel box is hiding something. Think about what that means. You have removed every particle. You have drained every trace of warmth. By every rule of the old world, the box should be silent, dark, and dead. A frozen nothing. Instead, something inside it refuses to be still. To understand why, we have to throw out the everyday picture of empty space and replace it with something far stranger. In the world revealed by modern physics, the vacuum is a surface, a living, humming surface that stretches through every corner of reality, through the box, through the room around you, through the vast dark between the stars. And that surface is never at rest. Physicists spent the last century learning to read it. What they found turned the emptiest thing imaginable into the most crowded, most violent, most energy-soaked place in the entire universe. They found that empty space carries a weight, a pressure, a hidden power that, by their own best math, should be strong enough to tear the cosmos to shreds. That power is real. We have measured a shadow of it in a laboratory, felt it push on solid metal, watched it nudge the light coming out of atoms. The vacuum is doing something, constantly, everywhere. And that leaves us with a mystery that has haunted physics for decades. A mystery hiding in the most ordinary thing there is. The empty space you move through every second of your life. Because when scientists finally sat down and calculated how much energy is packed into that humming vacuum, the answer came back so enormous, so absurd, so far beyond anything the universe actually shows, that many of them refused to believe their own equations. To see how the emptiest place became the biggest problem in science, we first have to understand what those humming surfaces really are, and why physicists became convinced that everything you have ever touched is built from them. Reach out and press your hand against the nearest solid surface. It feels firm, unbroken, real. Your hand stops because the table stops it. That is the whole story your senses tell you. Matter is stuff, and stuff is solid, and solid things fill space the way water fills a glass. Physics tells a different story, and it starts with a simple question. What is that table actually made of, all the way down? Break it into splinters, then grind the splinters into dust, then keep going. You reach molecules. Break those, and you reach atoms. Break an atom, and you find a tiny, dense core, wrapped in a cloud of electrons. Break the core, and you find protons and neutrons. Break those, and you find quarks. And there, at the smallest level we can reach, the solid world dissolves into something with no solidity at all. At that level, a quark is a ripple. An electron is a ripple, tiny traveling bumps on something that fills all of space. Physicists call that something a field. A field is one of the most powerful ideas in all of science, and the everyday version is easy to picture. Sprinkle iron filings around a magnet and they line up in curving arcs. They are tracing something invisible, a magnetic field, spread through the space around the magnet, carrying a strength and a direction at every single point. The field was there before you added the filings. The filings just let you see it. Now take that idea and push it as far as it will go. In modern physics, the magnetic field is one member of a huge family. There is a field for electricity, a field for every kind of particle you have ever heard of, an electron field, a quark field, a field for the particles of light. Each one fills the entire universe, present at every point, from the center of the sun to the emptiest gap between galaxies. And every particle in your body is a ripple on one of them. An electron is a tight little wave rippling through the electron field. A quark is a knot of energy traveling across the quark field. When two particles bump into each other, two ripples on two fields push on one another and change shape. The solid table under your hand is a vast, still pattern of ripples, humming together, holding their form. Here is the comparison that makes it click. Think of the ocean. The water is everywhere, filling the whole basin. A wave is the water itself, briefly rising and moving. Take the wave away, and the ocean is still there, flat and full. In the same way, take every particle out of the universe, and the fields are still there, spread through all of space, flat and silent and waiting. That is the real picture of the vacuum, an ocean of fields with all the waves removed, which raises the exact question that broke the old idea of empty space. If the fields are still there when every particle is gone, are they truly silent? Can an ocean ever lie perfectly flat, down to the very last drop? The answer, buried inside one of the strangest rules in physics, is a flat and startling no. And that single word is where the trouble begins. There is a rule in physics that sounds invented. It is one of the most tested, most trusted laws we have. It came from a young German physicist named Werner Heisenberg, working in the 1920s at the dawn of the quantum age. He was trying to pin down the behavior of the smallest pieces of the world, and he ran into a wall that would not move, a hard limit built into reality itself. Here is what he found. In the quantum world, you can never know everything about a particle at once. Measure exactly where something is, and you lose all grip on how fast it moves. Pin down its speed perfectly, and its position smears into a blur. The two facts trade against each other. Push one into sharp focus, and the other slides into fog. This is the uncertainty principle. The fuzziness lives inside nature itself, a feature of reality far deeper than any limit of our tools. Most people meet this rule as a fact about particles. Its deepest consequence is about empty space. Think about what perfect stillness would actually require. For a field to be truly flat, truly silent, it would have to sit at exactly zero strength and stay there, never moving, never changing. That means two things known at once with perfect certainty: the exact value of the field and the exact rate at which it changes, both nailed down, both frozen. The uncertainty principle forbids exactly that. Nature refuses to let any field hold a perfect, unchanging zero. Pin the value to zero with total certainty, and the rate of change blurs out of control. so the field compromises. It hovers near zero, but it jitters, it trembles, it flickers up and down around nothing, never settling, never resting, because resting is against the rules. Here is a comparison to hold on to. Imagine balancing a pencil perfectly on its sharp point, so still it never leans even a hair in any direction. In the ordinary world, a steady enough hand might come close. In the quantum world, that perfect balance is banned outright. The pencil must always be tipping, always wobbling, because absolute stillness would reveal too much at once. The vacuum is that pencil at every point in space, forever refusing to stand still, so the ocean of fields can never lie flat. Even with every wave stripped away, every particle gone, every trace of heat removed, the fields keep shivering. Tiny ripples appear and vanish on their own. The surface of empty space churns with a restless motion that has no cause and no off switch. It is the deepest reason our steel box in the void can never truly go quiet. And this shivering has a price. Movement carries energy. A trembling field holds more energy than a still one would, which means every point in empty space, every tiny patch of the vacuum, holds a small store of energy that can never be removed. Multiply that little store by all the points in space, and you begin to see the shape of the coming disaster. Because those numbers, once physicists dared to add them up, did not stay small. They grew and grew towards something monstrous. Every vibrating thing in nature has a lowest possible energy. Physicists call it the ground state. It is the quietest a system can ever be. For a child on a swing, the ground state is simple. Let the swing slow, and finally stop. It hangs straight down, motionless. Zero energy of motion, perfectly still. That is the bottom, and everyone expects the quantum world to have a bottom just like it. It does have a bottom. The bottom sits above zero. When physicists worked out the math for a tiny quantum vibration, they found a resting state that still moves. The lowest energy the system could reach was a swing that keeps swaying, ever so slightly, even at its calmest. A permanent minimum wiggle that can never be taken away. They gave this leftover energy a name: 0-point energy. The energy that remains at the point where all other energy is gone. Now here is where it grows teeth. A field can ripple in countless different ways at once. Long, slow, rolling waves that stretch across a room. Short, fast, tight little waves smaller than an atom. Every possible wavelength is a separate way for the field to vibrate, like a guitar string, humming many notes at the same time. Long notes, short notes, and every note in between. And each one of those countless notes carries its own 0-point energy, its own minimum hum that can never be switched off. So the vacuum holds a store of leftover energy for every possible wavelength, at every point in space, all at once, all the time. You can already feel the danger in that. The long, lazy waves each carry only a little energy. Fine, but the shorter the wave, the more energy it holds. A tight, fast ripple packs a bigger punch than a long, slow one. And there seems to be no flaw to how short a wavelength can get. You can always imagine one smaller and smaller and smaller still, each carrying more energy than the last. Picture a piano with an endless keyboard. The keys start low and stretch away forever toward higher and higher notes, and every key is being pressed, softly, all the time, all on its own. The low keys add a gentle hum, but the keyboard never ends. The high notes climb without limit, each louder than the one before, and they all sound together in a chord that grows and grows. That endless chord is the sound of empty space, according to the raw math. A vacuum humming on countless notes, each one adding to the total. This was the moment the trouble stopped being a curiosity and started looking like a threat. Because if every one of those notes is real, if the vacuum truly carries all that hidden energy, then empty space holds a staggering amount of power in every tiny pocket. The obvious next step was to add it all up, to take the piano with the endless keyboard and total the energy of every key, to ask a simple question with a terrifying answer: how much energy is actually sitting inside one small piece of nothing? But the hidden hum is more than abstract notes on a keyboard. It shows itself in a stranger form. The trembling vacuum is constantly giving birth to flickers of real matter, here and gone before anything can catch them. Right now, in the empty space around you, particles are being born out of nothing. They do not last. A tiny fraction of a second after they appear, they vanish again, paying back what they borrowed. But while they exist, they are as real as anything else. Physicists call them virtual particles, and they are one of the most bizarre predictions in all of science that also happens to be true. To see where they come from, go back to the trembling vacuum and the uncertainty rule, and add one more twist. That rule does more than blur position and speed. It also blurs energy and time. Over a long stretch of time, the energy of a patch of space stays fixed and steady. But over an incredibly short flash of time, the energy is allowed to blur, to become briefly more than it should. Nature lets empty space borrow a jolt of energy, as long as it pays that energy back fast enough that no one could ever catch the loan. And energy, famously, can turn into matter. This is the meaning of Einstein's most famous idea, that energy and mass are two forms of the same thing. So when the vacuum briefly borrows a jolt of energy, that energy can appear as a pair of particles. A particle and its mirror twin, its antiparticle, popping into being together. They live for the briefest instant. Then they slam back together, cancel out, and return the borrowed energy, leaving empty space, looking innocent again. Blink, and it has already happened 1,000,000,000,000 times over. This is happening everywhere, constantly, in the room around you, in the heart of a star, in the deepest void between galaxies, where nothing else exists. Empty space swarms with these fleeting pairs, appearing and vanishing faster than thought, a restless foam of matter flickering in and out of the dark. Here is a way to picture it. Imagine the surface of a pot of water just before it boils. Tiny bubbles form at the bottom, rise for an instant, and pop before they reach the top. From across the room, the water looks calm. Up close, it is alive with bubbles born and dying too quickly to follow. The vacuum is like that surface, except the bubbles are particles, and the boiling never stops. And there is no pot and no water, only space itself frothing with borrowed life. And these particles are far more than a fantasy. We see their fingerprints. They change the way real particles behave in ways we can measure to staggering precision. The math that includes this constant foam of virtual pairs makes predictions that match experiments to more decimal places than almost anything else humans have ever tested. The foam is real. Nature agrees. This is what turns the energy problem from strange to alarming, because all of this flickering, all of these borrowed particles, all of these humming notes on the endless keyboard carry energy, real energy, energy woven into the fabric of empty space, present in every cubic inch of the universe, impossible to remove because it is the lowest state there is. The vacuum, it turns out, is the most active place in existence, and it is holding a fortune in hidden energy. That raised a question no one could dodge. In Einstein's universe, energy is never weightless. Every scrap of it pulls on space and bends it. So if empty space is stuffed with energy, that energy should have weight. It should pull on the whole cosmos. And when one brilliant, sharp-tongued physicist first asked how hard, the answer he scribbled down was so ridiculous, he turned it into a joke. In Einstein's universe, energy is never weightless. This is one of the deepest lessons of his work on gravity. Anything that carries energy also carries a pull. Energy bends the space around it, warps the paths that things travel, tugs on everything nearby. Mass does this. And mass is only one form of energy. So light bends space, heat bends space, motion bends space, and the hidden energy humming in the vacuum, if it truly sits there, must bend space too. That single fact takes the vacuum puzzle and turns it into a cosmic emergency. Think it through. If every cubic inch of empty space carries a store of energy, and every scrap of energy pulls on the fabric of the universe, then empty space itself has a gravitational grip. The more energy packed into the vacuum, the stronger that grip. Fill space with enough hidden energy, and it would start to reshape the entire cosmos, curling it, crushing it, or blowing it apart. So the size of that hidden energy is far more than a technical detail. It decides the fate of everything. One of the first people to truly stare at this was an Austrian physicist named Wolfgang Pauli, one of the sharpest and most feared minds of the early quantum age. Pauli was famous for his brutal honesty. He once dismissed a weak idea by saying it was so bad it was not even wrong. He was exactly the kind of person to take a strange prediction seriously and chase it to its bitter end. So Pauli ran a rough calculation. He took the humming energy of the vacuum, the zero-point energy of the simplest case he knew, and asked what its gravity would do to the universe. How big could a universe even be if empty space weighed that much? The answer he reached was absurd. By his estimate, the gravity of all that vacuum energy would curl the entire universe into a ball so small it would not even reach out to the moon. The whole cosmos, every galaxy, every star, squeezed inside the gap between the Earth and its nearest neighbor in the sky. Pauli found the results so ridiculous, he treated it as a joke, a curiosity to share with friends, a sign that something in the reasoning must be off. But the joke had teeth, and it would not let go. Because Pauli had made no error, he was running the math exactly as the young science of quantum fields demanded. Every step was sound. Every rule was one that experiments would later confirm again and again. He followed good physics to a preposterous end, and instead of a mistake, he had caught the first glimpse of the deepest crack in our understanding of reality. For a while, physicists did what people often do with an uncomfortable result. They set it aside. The universe was obviously larger than the moon's orbit, so surely the vacuum energy simply did not weigh anything, or some unknown effect swept it away. The problem was filed under later. Later would take decades to arrive. First, physicists had to settle a more basic question, one that decided whether the whole idea was worth taking seriously at all. Was this humming vacuum energy actually real? Could you prove it existed and even measure it without appealing to the size of the sky? The answer came from a Dutch physicist: 2 polished metal plates and a force that pulls on nothing but the emptiness between them. Continuing with the body, chapters 7 through 17, each holds the punch pause rhythm, escalates from the last, and ends on a hook into the next. In 1948, a Dutch physicist asked a strange question about 2 mirrors facing each other in the dark. His name was Hendrik Casimir, and he worked at a research lab in the Netherlands, turning the puzzle of the humming vacuum over in his mind. He wanted to know if the hidden energy of empty space could ever be caught in the act, not just imagined, not just calculated, actually caught doing something real enough to measure on a laboratory bench. So he pictured 2 flat metal plates, carrying no charge, placed extremely close together inside a perfect vacuum, facing each other across a gap thinner than a human hair. Between them, nothing but empty space and its restless hum. Then Casimir noticed something clever. Remember the endless keyboard, the vacuum vibrating on every possible wavelength at once. Casimir realized that 2 close plates act like a filter. In the narrow gap between them, only certain waves fit, the ones whose length divides neatly into the space, the way a guitar string can only hold certain notes. Waves that do not fit are locked out of the gap. Outside the plates, though, every wavelength is welcome, with no gap to restrict them, so more vacuum waves press inward from the outside than push back from the inside. The 2 crowds do not balance, and the imbalance shoves the plates toward each other. The vacuum, in other words, would push 2 pieces of solid metal together with a real force. A force made of nothing but the difference between the emptiness inside the gap and the emptiness surrounding it. Here is a way to picture it. Old sailors told of two ships sitting side by side in a rolling swell, drawn mysteriously toward each other until they touched. The waves between the hulls were calmer, penned in by the ships, while the open sea outside heaved harder and pushed the vessels together. The plates are those two ships. The vacuum is the sea. This was a stunning claim. It said empty space could shove solid metal, that the great churning nothing could reach out and press on something. And Casimir gave a precise prediction to go with it. The closer the plates, the stronger the push, growing swiftly as the gap narrowed toward nothing. For years, it stayed a beautiful idea, too delicate to test. The force is unimaginably faint. Bring two plates within a fraction of a hair's width, and the pull between them amounts to less than the weight of a single speck of dust. To measure it, you would have to hold two surfaces almost impossibly flat and parallel, closer together than most instruments could manage, while blocking out every stray whisper of every other force in the room. Electric charges, vibrations from footsteps down the hall, the faint warmth of the equipment itself, any one of them could drown the signal completely. So the vacuum's push sat on paper, a prediction waiting for a machine delicate enough to feel it. Physicists believed it. The math was sound. But belief is one thing, and touching the force of empty space with your own instruments is another. For nearly 50 years, no one managed it. The idea grew famous and stayed unproven, a promise the vacuum had made that no one could yet collect on. Then, in a quiet laboratory near the end of the century, one physicist decided to stop waiting and actually feel the weight of nothing. In 1996, a physicist named Steve Lamoureux set out to measure a force that comes from empty space itself. He worked at an American national laboratory, and his key tool was a device of exquisite delicacy called a torsion balance. Picture a small rod hung from a single thin fiber, so finely balanced that the faintest sideways push sets it slowly twisting. The amount of twist reveals the size of the force. It is one of the most sensitive instruments ever built, able to feel a whisper of a shove. Lamoureux faced a practical nightmare. Keeping two flat plates perfectly parallel at a hair's width distance is nearly impossible. So, he used a clever swap. He replaced one flat plate with a gently curved surface, a sphere, coated in gold, and brought it creeping toward a flat, gold-coated plate until the two nearly kissed. A sphere and a plate do not need perfect alignment, which sidestepped the worst of the problem. Then came the hard part, hunting down every imposter. 1,000 other forces could fake the result. Leftover electric charge clinging to the gold, tiny vibrations shaking the room, shifts in temperature nudging the metal. He chased each one down, measured it, subtracted it, ruled it out, over painstaking months, until only one possible source of the twisting force remained, and the plates were drawn together. The fiber twisted. When Lamoureux measured the size of the pull, it matched Casimir's decades-old prediction. The vacuum was pushing, exactly as promised, and now the push had been felt and weighed. Other teams sharpened the measurement in the years that followed, and the result held firm. This is the closest we have ever come to touching the hidden energy of empty space. Two pieces of gold, nothing at all between them, drawn together by the restless churn of the vacuum, the foam of borrowed particles, the humming fields, the trembling that never stops. All of it leaves a mark you can measure with a twist of a fiber. Picture proving the wind is real without ever seeing it, by watching a blade of grass bend and knowing something invisible must be leaning on it. You never see the vacuum's energy directly. You see the gold move, and you know, this is what makes the coming problem so sharp. The energy of empty space had now been shown to shove solid metal in a laboratory, real enough to measure, real enough to trust, and by the rules of physics, energy that real must have weight. It must pull on the universe. The vacuum could no longer be waved away as a fantasy in the mathematics. The experiment slammed a door shut. From that point on, no one could stand up and claim the humming vacuum was imaginary and simply walk away from the problem. The energy was there. The only question left was how much of it, and what that amount would do to a universe. The plates were one fingerprint of the vacuum, a clear one, pressed into gold, but it was far from the only mark the churning emptiness leaves behind. There was another, stranger fingerprint, hidden somewhere far more intimate than a laboratory bench, inside the atoms that make up your own body, written in the light they give off. In 1947, a year before Casimir dreamed up his plates, another physicist caught the vacuum quietly tampering with light. His name was Willis Lamb, and he was studying hydrogen, the simplest atom in existence, one proton, one electron, circling each other. The established theory of the day made a crisp prediction about exactly where the electron's energy levels should sit, and therefore about the precise color of light the atom would give off. The math was clean, the forecast was sharp, the measurement disagreed, only slightly, but unmistakably. The energy levels were nudged, shifted by a whisker from where every equation said they belonged. A tiny gap had opened between theory and reality, and that gap had no business being there. The culprit was the vacuum. The electron circling the proton sits inside the churning foam of virtual particles, the flickering pairs that constantly boil in and out of empty space. Those fleeting particles jostle the electron endlessly, giving it a faint, permanent jitter, a tremble it can never shake off. That jitter shifts its energy by a hair, and the size of the shift matched Lamb's measurement almost perfectly. We call it the Lamb shift, and it stands as one of the first hard proofs that the vacuum foam is genuinely real and genuinely meddles with real matter. There is more. The electron behaves like a tiny magnet, and the exact strength of that magnetism is also tweaked by the swarm of virtual particles crowding around it. When physicists calculate that tweak, carefully including the whole boiling vacuum, and then measure it in the lab, the two agree to more than 10 decimal places. It is among the most precise agreements between prediction and experiment in the entire history of science. Imagine forecasting the exact time on a clock and being right down to the width of a single second across 1,000 years. That is roughly how well the mathematics of the humming vacuum matches the real behavior of matter. Now we are cornered. The vacuum energy shows up in the pull between metal plates. It shows up in the color of light from hydrogen. It shows up in the magnetism of a single electron, confirmed to a staggering number of digits. Every independent test points the same way. The foam is real. The hum is real. The energy woven into empty space is real, and the theory that describes it is one of the finest instruments humans have ever built, which drives us straight into the question no one can dodge any longer. If all that energy truly sits in every scrap of empty space, then exactly how much of it is there? Take the endless keyboard and add up every note. Take the boiling foam and total every flickering pair. Take the trembling fields and sum the whole restless surface of the vacuum. What is the grand total? Physicists finally sat down to do that sum, armed with the best theory they had. And the instant they tried, they slammed into a wall that had no top, a keyboard whose highest notes climbed upward forever, refusing to stop, driving the answer towards something no equation should ever produce. To weigh the vacuum, physicists had to add up the energy of every possible ripple inside it. That sum refused to end. Recall the endless keyboard, where every wavelength is a separate note and shorter waves carry more energy. There is no smallest wavelength, so the notes climb higher and higher without any ceiling, each one adding more energy than the last. Add them all honestly, note after note, and the total does not settle on a number. It races upward toward infinity. An infinite answer is a scream. In physics, when your equations hand you infinity, it means you have pushed them somewhere they were never built to go. Something in the setup is broken. So, physicists reached for a fix, a cutoff, a place to stop counting. The reasoning goes like this. Our current physics is not the final word. At some incredibly tiny scale, deeper than anything we have ever probed, the rules we know must break down and give way to a more complete theory we do not yet possess. So it makes sense to stop adding vacuum notes at that scale, trusting that whatever lies beyond follows different laws. Where should you stop? The natural place is a distance called the Planck length, the scale where gravity and quantum theory smash into each other and nobody knows the rules anymore. It is fantastically, absurdly small. Take an atom and shrink your view down as far below it as the atom sits below a whole city, and you are still nowhere close. The Planck length is smaller than an atom, by more than an atom is smaller than the entire solar system. At that scale, the smooth, familiar idea of space itself may fall apart. So, physicists cut the endless keyboard off at the Planck scale, stop the notes there, refuse to count any higher, and the sum finally becomes finite. A real, definite number emerges. You can add it all up and get an actual figure for how much energy is packed into a patch of empty space. Picture receiving a bill that would otherwise run forever and deciding to draw a line at the last item you actually understand, paying for what you can account for and leaving the fog beyond it as someone else's problem. That is what the cutoff does. It is a way to get a sensible answer out of a calculation that would otherwise spiral into nonsense. And this felt reasonable, conservative, even in the cautious sense. The Planck scale is the honest edge of everything we know, the frontier where our physics genuinely ends. Stopping there should give the most modest, most defensible estimate anyone could make for the energy of the vacuum. If anything, you might expect it to undershoot, since it ignores whatever wild energy might lurk in the unknown territory below. So, physicists had done everything carefully. They had faced the infinite sum, recognized the limit of their theory, and drawn the line at the most reasonable place in the universe to draw it. Every step was defensible. Every choice was cautious. Then they ran the number, and the most sensible, most conservative estimate anyone could possibly make came back so gigantic, so far beyond reason, that it made Pauli's shrunken universe from decades earlier look almost gentle by comparison. The answer came back as an energy packed into every cubic inch of empty space, and it was monstrous, beyond ordinary language. With the cutoff set at the Planck scale, the vacuum energy in a single tiny volume of nothing came out enormous past all reckoning. Every speck of emptiness, by this math, would carry a crushing store of energy. Empty space would be the densest thing in all of existence, each barren pocket of it heavier and more energetic than the blazing core of any star. The void, weighed honestly, would outweigh everything. This is the raw output of our best, most tested framework for how the smallest pieces of reality behave. The very same framework that pinned the electron's magnetism to more than 10 decimal places, that predicted the Lamb shift, that has passed every laboratory trial thrown at it. Turn that triumphant machinery loose on empty space, and it insists the vacuum is savagely, impossibly energetic. Recall the earlier lesson, the one that turns this from a curiosity into a crisis. Energy has weight. Energy pulls on space and bends it. So this monstrous figure is far from a harmless quirk of bookkeeping. It carries a gravitational grip. If the vacuum truly held that much energy, its gravity would seize the entire universe and do something violent and final to it. Imagine an architect who calculates, with flawless and careful arithmetic, that a small footbridge over a creek must be built to carry the weight of every ocean on Earth at once. Then he walks outside and finds a quiet wooden plank spanning the water, holding a person's weight without the slightest strain, exactly as footbridges always have. His math is perfect. His answer is deranged. Both things are true, and he cannot explain how. That is where physics stood, a prediction in hand, precise and enormous, produced by rules that work everywhere else. Now, all that remained was to compare it against the real universe, to look out at actual empty space and measure how much energy is truly sitting there. The universe does carry a faint energy in its emptiness. We can read it from the way the cosmos expands, and it is genuinely there, a real quantity woven into space. But it is unimaginably gentle, a whisper where the theory promised an all-destroying roar. The measured energy of the vacuum is a soft, barely there push, and the predicted energy is a scream loud enough to end creation. So physicists knew the vacuum, on paper, was almost infinitely heavy, while the real sky showed something delicate and small. The two numbers described the very same thing, the very same empty space. One came from the finest theory we own. One came from the universe itself. And the next question was simple and frightening. If empty space truly carried the energy the theory demands, what would that much power actually do to the universe around it? The answer is that there would be no universe left in which to ask the question. No stars, no galaxies, no planets, no you. The monstrous vacuum would have made sure of that in the very first instant of time. If empty space truly carried the energy our best theory predicts, you would not be here to wonder about any of it. To see why, you have to understand the peculiar way vacuum energy pulls. Ordinary matter's gravity draws things together. Stars, planets, dust, all of it clumps and gathers under a shared inward tug. But the energy of empty space works in reverse. Its strange gravity pushes space to stretch and grow. And the more of that energy there is, the faster space flies apart. Pack in the monstrous predicted amount, and the outward push becomes beyond violent. Follow that outward. In the first sliver of a moment after the universe began, space would have been ripped apart so ferociously that nothing could ever gather together. Every particle would be flung away from every other particle faster than any force could reel it back in. Matter would be scattered into a thin, cold haze before it had any chance to clump. No atoms drifting together, no clouds of gas collapsing into the first stars, no stars pooling into galaxies. The universe would have blown itself into an empty mist in less than the blink of an eye and stayed that way forever, a stretched and lifeless nothing. You, the Earth, the Sun, every galaxy scattered across the sky. All of it depends on empty space being gentle. In a universe where the vacuum weighed what the theory claims, none of it could exist. Imagine trying to build a sandcastle on a bedsheet while someone yanks that sheet outward in every direction at once. The grains scatter and fly before your hands can shape a single tower. That is a universe with a heavy vacuum. The building blocks are thrown apart before anything can ever be built. So, the prediction is worse than merely inaccurate. It is catastrophically, existentially wrong. If it were correct, there would be no galaxies, no planets, no chemistry, no living things, and no physicists to write the equation that produced it. The plain fact that a single star exists, that anything exists at all, stands as proof that the vacuum does not weigh what our mathematics insists it must. And that is the trap closing tight. The mathematics is our finest mathematics, the same rules that passed every laboratory test with breathtaking precision. Yet aimed at empty space, those same rules predict a universe that could never have formed a single star in a cosmos visibly overflowing with them. Physicists were left with a prediction so wrong it should be easy to discard, produced by a theory so successful it cannot be discarded. Both things were true at once, and no one could make them fit. So, they were forced to ask the harder question: what is the vacuum energy actually, out in the real cosmos, measured from the sky rather than scribbled on paper? By the closing years of the 20th century, they finally had a way to find out by watching how the true universe expands across billions of years. What they measured was not the destroying roar the theory demanded. It was a faint, stubborn, non-zero whisper, and that gentle whisper, delicate as it was, would transform a comfortable old embarrassment into the deepest unsolved mystery in all of science. Out in the real universe, empty space carries a hidden energy, and we have measured how much. The clue is written in the expansion of the cosmos. Every patch of empty space carries a faint outward push, and that push reveals itself in the way distant galaxies drift apart over enormous spans of time. By carefully tracking how the universe stretches, cosmologists can read off exactly how much energy the vacuum actually holds. The sky becomes a scale, and empty space steps onto it to be weighed. The reading is real, and it is astonishingly gentle. Spread the energy of the entire vacuum across an ordinary room, and it would amount to less than a whisper, a trace so slight it barely registers. Empty space carries a tiny positive energy, just enough to give the whole cosmos a faint, patient outward push over billions of years, and hardly anything more. This soft whisper is the number the theory was always meant to predict. This is the target, a delicate, almost nothing energy, real but barely there. And the theory, running its flawless and celebrated machinery, took aim at that gentle target and produced a result powerful enough to annihilate the universe. Picture asking a master marksman to lay a dart down softly on a board just an arm's length away, the easiest shot imaginable. Then watch him fire it clean through the wall, through the building behind it, and out past the curve of the horizon. The target was soft and close. The shot was apocalyptic. That is the theory and the sky, aiming at the same gentle mark. Now the two numbers sat side by side for everyone to see. The predicted energy of the vacuum, gigantic past all reason. The measured energy of the vacuum, a barely detectable whisper in the expansion of space. The same quantity, the same empty space. One handed down by the finest theory we possess, one read straight from the universe itself, and the distance between those two numbers was about to be named. A gap so vast it has become legendary among physicists, a single figure they bring out to humble anyone who imagines we truly understand the cosmos we live in. The measured whisper and the predicted roar are not close. They are not within reach of each other by any stretch of any imagination. To capture how far apart they are, you would have to write down a number so large that it dwarfs the everyday words we use for bigness. Huge fails, enormous fails. The gap sails past them all. When you take the enormous prediction and divide it by the gentle reality, you get a single, staggering figure, and that figure has earned itself a grim and famous title, spoken with a kind of dark pride by the very people whose theory produced it. They call it the worst prediction in the history of science. Here is the number that haunts physics. The predicted energy of the vacuum is larger than the measured energy by a factor of 1 followed by roughly 120 zeros. Say it slowly. The prediction is not 120 times too big. It is a 1 with 120 zeros trailing behind it times too big. Written out in full, that number would run clear off the edge of any page you tried to fit it on. It is a gap so wide that ordinary words like huge or vast or enormous simply crumble against it. Physicists have names for this wound. Some call it the cosmological constant problem. Some call it the vacuum catastrophe. Many just call it the worst theoretical prediction ever made, because in all the long centuries of science, no other calculation has ever missed reality by so far. What makes it sting so deeply is where the prediction comes from. This grew out of quantum field theory, the crown jewel of modern physics, the framework behind nearly everything we understand about particles and forces, the very math that pinned the electron's magnetism to more than 10 decimal places. That battle-tested, triumphant theory aimed at the simplest thing in all of existence, empty space, missed the answer by more zeros than most people can even picture. Imagine the most reliable friend you have ever known, someone correct about everything for a lifetime, trustworthy, down to the smallest detail. Then one day that friend looks at the coffee cup on your desk and swears, with total confidence and airtight reasoning, that it weighs more than every star in the sky combined. The reasoning checks out at every step. The conclusion is madness. That is quantum field theory and the vacuum. And the mismatch is stubborn. It refuses to be a small correction waiting quietly for a patch. Physicists have hurled decades of their sharpest ideas at it. New symmetries in nature, undiscovered particles, extra hidden dimensions of space, whole imagined oceans of other universes. Every attempt has fallen short of an answer that convinces everyone. The one with 120 zeros still stands there, unexplained, planted squarely at the center of physics. This is the strange humiliation at the heart of our understanding. We have a theory that works magnificently, tested to breathtaking precision, that also delivers the single most spectacular failure ever recorded. Both facts are carved in stone. Nobody can fully reconcile them. To even begin grasping the size of the number, comparisons to everyday things fall apart almost the instant you try. Coffee cups and oceans and stars are far too small to carry the weight of it. So to feel the true scale, you have to reach for the largest thing there is to reach for, the entire universe, counted piece by piece. Because the mismatch turns out to be larger than the total number of atoms in everything we can see, larger than the count of every particle of matter in the visible cosmos. And once that comparison sinks into place, the real, dizzying scale of the failure finally swims into focus. To feel how large a one with 120 zeros really is, start by counting atoms. Take a single grain of sand. It already holds more atoms than you could count in 100 lifetimes. Now take every grain of sand on every beach on Earth and count all their atoms too. Then add every drop of water in every ocean, then the whole planet beneath them, atom by atom, all the way down to the iron core, then the sun, 1,000,000 times larger than the Earth, then every star burning in our galaxy, hundreds of billions of them, then every galaxy scattered across the visible universe, hundreds of billions more, each stuffed with its own hundreds of billions of stars. Add up every atom in everything we can see, from here to the farthest edge of the observable cosmos. The grand total comes to roughly a 1 followed by 80 zeros. That single number counts all the matter in all the stars and planets and gas clouds in the entire visible universe. The vacuum mismatch is bigger than that, vastly bigger. To climb from a 1 with 80 zeros up to a 1 with 120 zeros, you would take the count of every atom in the whole visible universe and then multiply it again by an immense number carrying 40 more zeros on top. The size of the prediction's failure outweighs, in raw magnitude, the tally of all the matter that exists. So, the predicted vacuum energy and the measured vacuum energy stand impossibly far apart. They sit in different worlds, different realms, separated by a gulf wider than the count of everything there is to count. When physicists say the theory missed, they mean it missed by more than the number of atoms in the sky. This is the part that keeps physicists awake at night. A theory this wrong ought to be simple, to throw in the bin and forget. But quantum field theory refuses to be wrong. It works. It is one of the most successful and precisely tested ideas humans have ever produced, confirmed again and again across countless experiments. So we are left clutching a single theory that is at once our greatest triumph and the author of our greatest catastrophe, and no one alive can fully explain how it manages to be both. For a long stretch, physicists held onto a comforting escape hatch. Perhaps the true energy of the vacuum is simply zero. Perhaps some perfect, hidden cancellation wipes the whole monstrous number clean out of existence, deleting it down to nothing, leaving empty space genuinely weightless after all. If the vacuum weighed nothing, there would be no catastrophe to explain. The problem would quietly dissolve. That comforting hope had deep roots. It traced all the way back to a single mysterious term that Albert Einstein himself once wrote into the laws of gravity, and then spent years of his life wishing he had never touched. To understand why the vacuum could not simply be zero, and why that hope eventually collapsed, we have to return to the man who first added the energy of empty space to physics, and then called it the greatest blunder he ever made. In 1917, Albert Einstein sat staring at his own equations, and they were telling him something he flatly refused to believe. He had just completed his masterwork, a revolutionary new theory of gravity that described how matter and energy bend the very shape of space. Eager to test its reach, he turned it loose on the biggest thing imaginable, the entire universe at once. And the equations came back with a verdict he could not accept. The universe could not sit still. Gravity should be dragging all its matter together, So a static, unchanging cosmos should be collapsing inward under its own weight. In 1917, though everyone believed the universe was eternal and unchanging, Einstein among them, a collapsing cosmos was unthinkable, so he added something to his equations by hand, a single extra term he could tune to push outward against gravity's inward pull, holding the universe in perfect balance so it neither collapsed nor blew apart. He called it the cosmological constant, and in plain terms it amounted to a built-in energy of empty space, a gentle outward push woven into the vacuum itself. That is the crucial link. Einstein's cosmological constant was, in modern language, exactly the energy of the vacuum, the very quantity that would later become a catastrophe. He had introduced empty space's hidden push into physics deliberately, as a fudge, purely to keep the universe standing still. Then reality intervened. In 1929, the astronomer Edwin Hubble peered through a telescope and found galaxies streaming away from us in every direction. The universe was expanding all along. It had never needed propping up. Worse still, had Einstein simply trusted his original equations, he might have predicted that expansion years before anyone observed it, which would have ranked among the greatest forecasts in the history of science. Instead, he had covered it up with a term he never needed. So Einstein removed the constant, set it firmly to zero, and, by one famous account, called it the greatest blunder of his life. For decades afterward, most physicists followed his lead without hesitation. They fixed the vacuum energy at exactly zero and moved along. Empty space, they assumed, simply weighed nothing at all, and the monstrous prediction pouring out of quantum theory must somehow be cancelled to nothing by a rule not yet discovered. Picture a builder who bolts a heavy support beam under a house he fears will sag, only to discover the house was standing perfectly well on its own the whole time. Embarrassed, he quietly unbolts the beam and carries it away, wishing he had trusted the structure from the start. That was Einstein, and his constant, added in fear, removed in regret. Setting the vacuum energy to zero was wonderfully convenient. It made the whole catastrophe evaporate, at least in spirit. If empty space weighed nothing, there was no monstrous energy left to account for, and the awful mismatch could be filed away as a headache for some distant future generation to sort out. For nearly 70 years, that comfortable assumption quietly held. Empty space weighed nothing, the textbook said, and physics moved on. Then, in the closing years of the 20th century, two rival teams of astronomers aimed their telescopes at exploding stars in the deep, distant universe. And what they saw out there dragged Einstein's abandoned term violently back to life. In the late 1990s, two rival teams of astronomers were racing each other to measure how fast the universe was slowing down. Everyone already knew the shape of the answer. The universe had been expanding ever since the Big Bang, and the combined gravity of all the matter inside it should be steadily hauling everything back, gently braking that expansion. The only real question was how hard the brakes were pressing. Would gravity eventually win and drag the whole cosmos back into a fiery crunch, or would the expansion merely slow down and coast onward forever? To settle it, the teams needed a way to measure both distance and speed across billions of years of cosmic history. Their tool was a particular kind of exploding star. One special type of supernova always detonates with very nearly the same true brightness, which makes it a dependable cosmic yardstick. Measure how bright such an explosion appears from Earth. Compare that to how bright it truly is, and its distance falls right out of the difference. And because light takes so long to cross the cosmos, catching these explosions far away means looking deep into the past, reading the expansion as it was billions of years ago. Both teams gathered their distant supernovae. Both teams checked and rechecked, and both found the same startling thing. The far-off explosions were dimmer than they should have been, fainter, which meant farther away than anyone expected, which meant the expansion of the universe had not been slowing down over the eons. It had been accelerating, stretching outward faster and faster as time went on. This overturned what nearly every scientist believed. Two competing groups, each half hoping to catch the other in a mistake, arrived independently at the same impossible result. Something out there was pushing the universe apart, overpowering the combined inward pull of all its matter and growing stronger as space itself grew larger. Imagine tossing a ball straight up into the air and watching it rise, then rise faster, then suddenly rocket upward toward the clouds instead of falling back into your hand. Every instinct screams that it should slow, stop, and drop. Instead, it flies away, accelerating into the sky. That is exactly what the universe was doing, and it made no sense under the old rules. There was, though, one thing in all of physics that could push space to expand faster and faster, an energy built into the vacuum itself, pressing outward everywhere at once, precisely the kind of term Einstein had added long ago and then thrown away in shame. His abandoned constant had been right all along. Empty space did carry a hidden energy after all, faint but genuine, and now it had been caught red-handed, stretching the entire cosmos apart before the astronomers' eyes. The discovery reshaped the whole science of cosmology almost overnight, and years later it earned its finders the highest prize in science. The vacuum energy Einstein had buried, the quantity physics had set to zero for 70 years, was suddenly, undeniably real. But identifying the culprit turned out to be far harder than catching it in the act. Physicists now held a force with no face and an energy with no clear source, filling all of space and driving the galaxies apart. They needed a name for it, and the name they chose quietly confessed just how little they truly understood. Physicists had caught an invisible force stretching the universe apart, and they had almost nothing to say about what it was. They could measure it. They could track its push across billions of years. They could calculate how much of it filled the cosmos. But when it came to the simplest question, what actually is this thing? They were empty-handed. So they gave it a name that quietly admitted their ignorance. Dark energy. The word dark here means hidden, unknown, unseen. A label for a blank space in our understanding. And that blank space turned out to be most of the universe. When cosmologists tallied up everything the cosmos is made of, the results were humbling. All the ordinary matter, every atom in every star, planet, cloud, and living body adds up to only about 1 part in 20 of the whole. A larger slice, roughly a quarter, is another mystery called dark matter, an unseen substance whose gravity holds galaxies together. And the rest, the overwhelming majority, close to 7 parts in 10 of everything that exists, is dark energy, the push in the vacuum, the thing with no face. Sit with that for a moment. Nearly 70% of the entire universe is made of something we cannot see, cannot catch, and cannot explain. Everything you have ever looked at, every star mapped, every galaxy photographed, all of it together is a thin sliver floating on an ocean of the unknown. The cosmos is mostly a substance we named out of pure ignorance. Picture opening a treasure chest that fills an entire warehouse and finding that all the gold and jewels you can see amount to a single coin in one corner. The rest of the warehouse, floor to ceiling, wall to wall, is packed with sealed boxes you cannot open and have no way to peer inside. That is our inventory of the universe. One shining coin of familiar matter, adrift in a warehouse of the dark. Now the mystery had a shape, and it lined up with an old ghost. Dark energy behaves exactly like an energy woven into empty space, pushing outward everywhere at once, which is precisely what Einstein's abandoned constant described, which is precisely what the humming quantum vacuum was supposed to provide. 3 separate threads, an astronomer's measurement, a discarded term in Einstein's equations, and the churning energy of empty space all seemed to point at one single thing, and that apparent unity was thrilling. For a brief, hopeful moment, it looked like the pieces might click together. Maybe the mysterious dark energy accelerating the universe simply was the vacuum energy of quantum theory, finally showing its face on the cosmic stage. Maybe the catastrophe was not a failure at all, but a clue, and these two great puzzles were secretly one puzzle wearing two masks. If dark energy and vacuum energy were the same thing, then quantum theory had, in a sense, predicted the accelerating universe all along. The push was real. The source seemed obvious. All that remained was to check whether the numbers matched. So physicists lined them up. The measured strength of dark energy on one side, the predicted strength of the vacuum energy on the other. Two numbers describing what might be the very same force. And the instant they compared them, the beautiful unity shattered into the worst disagreement in the history of science. For one exhilarating moment, it looked like two of the deepest mysteries in physics might collapse into a single answer. On one side stood dark energy, the unseen push accelerating the universe, discovered in the light of distant exploding stars. On the other stood the vacuum energy of quantum theory, the hidden hum woven into empty space, proven real by the pull between metal plates and the wobble inside atoms. Both were energies belonging to empty space itself. Both pushed outward, both filled every corner of the cosmos evenly. On the surface, they looked like twins. The logic was almost too clean to resist. Quantum theory insists empty space carries energy. Einstein's gravity insists that such energy pushes space to expand. The astronomers had caught space expanding faster and faster. So perhaps the humming quantum vacuum was the engine behind the acceleration, and dark energy was simply the vacuum energy, seen from far away and given a new name. One source, one explanation, two puzzles solved in a single stroke. Physicists have a deep love for this kind of unification. Again and again, the greatest leaps in science have come from realizing that two things thought to be separate were secretly the same. Electricity and magnetism turned out to be one force. Space and time turned out to be one fabric. So the dream that dark energy and vacuum energy were one and the same fit a proud and successful pattern. It felt like the shape of a real answer. Picture a detective who has spent years working two unsolved cases in two different cities and suddenly realizes the same culprit is behind both. What looked like two impossible mysteries becomes one solvable story. That is the hope that gripped physics. The vacuum was the single suspect standing behind both crimes. There was only one way to test the idea, and it was brutally direct. If dark energy truly is the vacuum energy, then the amount of dark energy measured out in the sky must match the amount of vacuum energy predicted by quantum theory. The number read from the expanding universe had to line up with the number calculated from the humming fields. Same thing, same value. That is what being the same thing means. So physicists set the two numbers side by side and looked. The measured dark energy was the gentle whisper, the faint outward push that stretches the cosmos slowly across billions of years. The predicted vacuum energy was the monstrous roar, the one with 120 zeros, the energy powerful enough to have torn the young universe to shreds. The gentle whisper and the world-ending roar were supposed to be the very same number. They were not close. They were separated by that same staggering gulf, larger than the count of every atom in the visible universe. The beautiful dream of unification did not just wobble, it detonated. The two puzzles refused to merge. Instead, joining them made everything worse. Now, physicists had a real dark energy of a very specific, very tiny size that genuinely fills the cosmos, and a theory that predicts a vacuum energy of a wildly, impossibly different size that ought to fill the very same cosmos. The mismatch was no longer an abstract worry on paper. It was nailed directly to something we had actually measured in the sky, which forced a far more disturbing question into the open. If the vacuum really does carry that monstrous energy, then how, by what miracle, does the real universe hide almost every last drop of it? Here is the escape route physicists were forced to consider, and it is stranger than the problem itself. The vacuum energy from quantum theory is not a single number. It is a sum of many separate contributions, each field in nature adding its own share to the total. The electron field contributes. The quark fields contribute. The fields of light and force all pour in their piece. And, crucially, some of these contributions come with a plus sign, pushing the total up, while others come with a minus sign, pulling it down. The final vacuum energy is what remains after all of them are added together. That opens a possible door. What if the huge positive contributions and the huge negative contributions very nearly cancel each other out? What if the monstrous roar from one field is almost perfectly erased by an equally monstrous roar from another, leaving behind only the faint whisper we actually measure? At first, this sounds like a rescue, but look closer at what it demands, because the demand is monstrous in its own right. Each contribution is enormous, carrying that full staggering size with 120 zeros. For them to cancel down to the tiny measured whisper, they would have to match each other, plus against minus. Not just roughly, not just closely, but to something like 120 decimal places. The positive pieces and the negative pieces would have to agree, digit for digit, through more than 100 places past the decimal point, and only then, at the very tail end, fail to cancel by the smallest sliver, leaving the delicate dark energy behind. Physicists call this fine-tuning, and this is the most extreme case of it anyone has ever found. To feel how absurd that precision is, imagine two vast mountains of sand, each holding a number of grains beyond all counting, sitting on opposite sides of a scale. For the scale to balance out to a single grain, the two mountains would have to contain exactly the same number of grains through more than 100 matching digits, differing only by one grain at the very end. Build the mountains blindfolded, pouring the sand by chance, and the odds of landing that close are beyond vanishing. Yet the universe appears to have done exactly that. This is what makes the vacuum catastrophe so maddening. Setting the energy to zero would at least feel clean, a perfect cancellation down to nothing. But the universe did not choose zero. It chose a value almost unimaginably close to zero, and then stopped just short, leaving a faint, deliberate-looking whisper of dark energy behind. Not nothing, but very nearly nothing, tuned to a razor's edge. A number balance that finally cries out for a reason. In physics, when a quantity comes out fine-tuned to 100 decimal places, it almost always means a hidden mechanism is doing the balancing on purpose, some deeper rule enforcing the cancellation. Blind luck at that precision is a possibility no physicist can comfortably accept. So the hunt began for that hidden mechanism, for some principle of nature that could force the vast positive and negative energies to slaughter each other almost exactly, leaving the tiny remainder we live in. And the most beautiful candidate ever proposed came from a stunning idea that every particle in existence might have a secret partner, a shadow twin built precisely to cancel it out. There is an idea in physics so elegant that many scientists were sure it had to be true. It is called supersymmetry. To see its power over the vacuum, start with a curious fact about the two great families of particles. Nature sorts its particles into two camps. One camp includes the particles of matter, things like electrons and quarks. The other includes the particles that carry forces, things like the particle of light. And here is the key. When these two camps contribute their energy to the humming vacuum, they do so with opposite signs. The matter particles push the vacuum energy one way, the force particles push it the other way. Supersymmetry takes that hint and runs with it in a breathtaking direction. It proposes that every particle in existence has a partner in the opposite camp. Every matter particle has a shadow force partner. Every force particle has a shadow matter partner, a perfect pairing, each particle matched to a twin built to push the vacuum energy in the exact opposite direction. Now watch what that pairing does to the catastrophe. Each particle pours its monstrous contribution into the vacuum energy, but its shadow partner pours in an equally monstrous contribution with the opposite sign. The two twins meet and cancel, plus against minus, perfectly, exactly. Do this for every particle and its partner across all of nature, and the enormous positive and negative energies annihilate each other completely. The whole monstrous vacuum energy collapses cleanly, all the way down to zero. This was the dream, not a fine-tuned cancellation balanced on a razor's edge by luck, but an automatic one, guaranteed by a deep symmetry woven into nature. Supersymmetry would make the great cancellation effortless and exact, forced by the very structure of reality. The worst prediction in physics would dissolve on its own. Picture a perfectly balanced mobile hanging from a ceiling, every arm matched by an equal arm on the opposite side, every weight answered by a twin weight across the pivot. It hangs level not by careful adjustment but by pure symmetry of design. Supersymmetry promised a universe balanced exactly like that, the vacuum energy zeroed out by the flawless matching of every particle with its shadow. The idea was so elegant and solved so many problems at once that for decades it was the leading hope for the next great leap in physics. Thousands of scientists devoted their careers to it. Enormous machines were built partly to hunt for those shadow partners. If supersymmetry were real, the largest particle colliders on Earth should be able to conjure the twin particles into existence, and physicists waited eagerly to catch the first one. There was, however, a fatal catch hiding inside the beautiful symmetry, and it came down to a simple observation about the world. If every particle truly had a shadow partner of equal mass, we would have found those partners long ago. An electron's twin, light enough to match the electron, would turn up easily in experiments. Yet no such twins have ever been seen, not one, which means that if supersymmetry exists at all, its perfect balance must already be broken. The twins shoved up to masses far heavier than the particles they mirror. And a broken symmetry, it turns out, cannot deliver a perfect cancellation. The beautiful rescue had a fatal flaw, and it was hiding in plain sight. If supersymmetry were exact, every particle's shadow partner would weigh exactly the same as the particle itself. An electron's twin would be as light as an electron, and a partner that light would be easy to create and catch in experiments. We would have discovered a whole mirror family of particles decades ago. Filling out the tables of physics, we have found none of them. The most powerful particle colliders ever built have searched exhaustively, smashing particles together at tremendous energies, hunting for even a single shadow twin. The searches have come up empty. If those partners exist, they are far heavier than the particles they mirror, hiding at energies beyond what our machines have reached. That single fact wrecks the perfect cancellation. Supersymmetry only zeroes out the vacuum energy when each particle and its twin have matching masses, so their contributions cancel exactly. But if the twins are much heavier, the match is spoiled. The particle and its shadow partner no longer push the vacuum energy by equal and opposite amounts. The plus and the minus stop lining up. A remainder survives. So the great cancellation becomes partial instead of total. The vacuum energy shrinks, but it does not vanish, and when physicists estimate how much survives, given how heavy the missing partners must be, the leftover is still catastrophic. Enormously smaller than the raw prediction, yes, but still vastly, hopelessly larger than the gentle whisper the universe actually shows. Picture that perfectly balanced mobile again. Every arm matched by an equal weight across the pivot, hanging level and serene. Now make the weights on one side much heavier than their partners on the other. The whole structure lurches and tilts, thrown violently off balance. That is broken supersymmetry. The elegant zero collapses, and a large imbalance comes crashing back. This was a bitter disappointment. Supersymmetry had been the great hope, the elegant idea that would tame the vacuum, explain the fine-tuning, and open the door to deeper physics. And instead of finding its shadow partners, physicists found empty-handed silence. Experiment after experiment. The symmetry, if it exists at all, is broken badly enough that it cannot solve the very problem it was meant to solve. The vacuum catastrophe simply refused to die. Every elegant tool physicists reached for either failed outright or left a mismatch still far too large to ignore. The problem sat there, unmoved, swallowing beautiful theories whole and handing back nothing. At this point, some physicists began to wonder whether they had been asking the wrong kind of question all along. Maybe there is no hidden mechanism forcing the vacuum energy to a small value. Maybe there is no elegant symmetry waiting to be found. Maybe the reason the vacuum energy is small enough for us to exist is far stranger and far more unsettling than any tidy law of nature. Maybe the answer is that we live in one universe among an unimaginable multitude, and the only reason we find ourselves in a gentle one is that a violent one would have no one inside it to look. In 1987, a physicist named Steven Weinberg made a prediction using logic so strange it barely felt like physics at all. Weinberg was one of the towering figures of the field, a man who had helped build the very framework that now produced the catastrophe. He looked at the vacuum energy problem and made a daring move. Instead of hunting for a hidden mechanism to force the energy small, he asked a different question entirely. What values of the vacuum energy would even allow living things to exist and wonder about it? The reasoning runs like this. The vacuum energy controls how fast space is pushed apart. Make it large and positive, and space would fly apart so violently that matter could never gather. No galaxies would form. No stars, no planets, no life. Any universe with a big vacuum energy would be a sterile, scattered haze with no one inside it. Only a universe with a very small vacuum energy could ever grow galaxies, and therefore only such a universe could ever contain observers. Now add one more radical idea. Suppose our universe is a single bubble among an unimaginable number of other universes, each one born with its own random value of vacuum energy. Most of those universes would have large values and stay barren forever. A rare few would happen to have tiny values, small enough for galaxies and stars and life to appear. In that vast collection, where would you expect to find yourself? Only in one of the rare, gentle universes, of course, because those are the only ones with anyone in them to ask the question. You could no more find yourself in a barren universe than a fish could find itself living on dry land. The very fact that you exist filters out all the violent universes automatically. This is the anthropic reasoning, and Weinberg pushed it to a sharp point. If this picture is right, he argued, the vacuum energy we measure should be small, but probably not exactly zero. It should sit right around the largest value that still permits galaxies to form, since that range covers the most universes where observers could arise. He essentially predicted a small, non-zero vacuum energy, roughly in a particular range, years before dark energy was discovered. Then, in the late 1990s, the exploding stars revealed dark energy, and its measured value landed remarkably close to what Weinberg's strange logic had suggested. Picture drawing a single ticket from a barrel holding countless lottery numbers, and being astonished to find you hold a winning ticket. Then realize the barrel only ever hands tickets to winners, because losers never get to reach in. Your winning ticket suddenly seems far less miraculous. That is the anthropic answer. We hold a rare, gentle universe, only because gentle universes are the only ones with hands to draw the ticket. It is a genuinely clever idea, and it fits the measured number uncomfortably well. Weinberg's prediction, born from pure survival logic, roughly hit a target that beautiful mechanisms had failed to explain for decades. Yet for many physicists, this answer felt less like a triumph and more like a quiet defeat. Because if it is true, it means the deepest features of our universe might have no elegant explanation at all, only the cold accident of which bubble we happen to be born in. And that possibility split the world of physics into two warring camps. Weinberg's idea handed physics an answer that many scientists found almost unbearable to accept. The trouble is what the answer requires you to swallow. It asks you to believe in a vast collection of other universes, each with its own settings, nearly all of them forever beyond our sight. We cannot travel to them, we cannot see them, we cannot detect them in any instrument. They sit, by their very nature, outside the reach of every experiment we could ever perform. And that raises a hard question about whether the idea belongs to science at all. Science lives and dies by testing. A good explanation makes a prediction you can check against the world, and reality gets to say, yes or no. But how do you test a claim about universes you can never observe? If the answer to the vacuum mystery is simply that countless invisible universes exist, and we happen to occupy a rare, gentle one, then the explanation seems to float beyond the reach of proof, which is exactly where many physicists refuse to follow. So the field split into two camps, and the argument between them grew heated. One camp embraces the multiverse. To them, it is a natural consequence of ideas physicists already take seriously, including certain theories of how the early universe expanded and certain frameworks from the deepest levels of particle physics. If those theories are right, they argue, then a multitude of universes may simply come along for the ride, whether we like it or not. The gentle value of our vacuum energy needs no elegant law. It is just where we happen to live. The other camp recoils. To them, invoking unseeable universes to explain a number feels like surrender dressed up as insight. They argue it explains everything, and therefore nothing, that once you allow infinite, invisible universes with every possible setting, you can wave away any mystery at all, without ever learning why. They hold out for a real mechanism, a genuine law of nature still waiting to be discovered, one that would predict the vacuum energy from solid principles and could actually be tested. Picture two groups of explorers standing at the edge of a canyon they cannot cross. One group says the far side surely holds cities they can infer but never visit, and treats those unseen cities as real. The other group insists that whatever cannot be reached and checked should not be counted as known at all. Both are staring at the same canyon. Neither can walk across it. And their disagreement is not really about the canyon, but about what counts as knowledge. This argument is still raging today, with brilliant physicists lined up firmly on both sides, and no experiment in sight to settle it. The vacuum energy sits at the center of one of the deepest rifts in modern science, a rift not merely about one number, but about the limits of what science can ever hope to explain. And while that war over the multiverse burns on, a smaller, quieter group of physicists has been making a very different and far more subversive claim. They suggest that the entire catastrophe may rest on a mistake, that the monstrous prediction everyone has been trying to explain away for decades was never a real prediction in the first place. While most physicists fought over how to explain the monstrous vacuum energy, a smaller group began quietly asking whether it was ever really there. Their argument is subtle, and it strikes at the root of the whole problem. They point out that the energy of the vacuum, on its own, may not actually do the thing everyone assumed it does. The whole catastrophe rests on one crucial link, that the humming energy of empty space must gravitate, must pull on the fabric of the cosmos, must push space to expand. Take away that link, and the monstrous number, however large, would simply have no effect on the universe, and there would be nothing left to explain. These physicists argue that the leap from vacuum energy to cosmic gravity was never as solid as it seemed. In the everyday physics of particles, only differences in energy tend to matter, not the total amount. The Casimir plates, for instance, feel a force because the energy between them differs from the energy outside them. The overall sea of vacuum energy, the vast constant background, never shows itself in those experiments at all. So perhaps, they suggest, that vast background does not gravitate either, and the whole apocalyptic prediction was a mirage born of taking a bookkeeping quantity too literally. In this view, the famous number with 120 zeros is not a real prediction that failed. It is an artifact, a piece of mathematical scaffolding that was never supposed to be read as the actual weight of empty space. The true energy that does gravitate, the one that shows up as dark energy, is simply a separate quantity we read from the sky, and quantum theory never claimed to predict it in the first place. Picture a shopkeeper who writes down the full sticker price of every item in the store, a colossal grand total, and then panics that he must somehow possess that much cash on hand. A calmer colleague points out that the sticker total was never money he owed. It was just a number on a page, never meant to be paid. The heretics are saying the vacuum catastrophe is a bill that was never actually due. This is a genuinely serious position held by some very sharp physicists, and it would dissolve the whole crisis in a single stroke. If the vast vacuum energy does not gravitate, then there is no monstrous mismatch, no worst prediction in history, only a small dark energy read from the sky and waiting for an ordinary explanation. But the position is far from settled, and it has its own deep difficulties. The connection between energy and gravity is one of the most thoroughly tested ideas in all of physics, confirmed everywhere we look. Claiming that one particular kind of energy quietly ignores gravity, while every other kind obeys it faithfully, is a bold move that demands its own careful justification. And so the debate goes on, unresolved. Whether the catastrophe is a true crisis or an elaborate misunderstanding, all these arguments circle back to one thing we can actually study: the real, physical state of the vacuum, its true shape, its true bottom. Because empty space, it turns out, is not a featureless void at all. It has a landscape, and the exact shape of that landscape may decide the fate of everything. Empty space has a shape, a hidden landscape that decides how the vacuum behaves, and reading that shape may be the key to everything. To picture it, return to the idea of fields filling all of space, and focus on one field in particular, the one that gives many particles their mass. That field has a value at every point in the universe. And here is the strange part. Unlike most fields, which rest at zero when left alone, this one settles at a particular non-zero value everywhere, all the time, a permanent background level woven into empty space. The vacuum we live in is defined by that resting value. Now, why does the field rest at that specific value and not some other? The answer is captured by a landscape, an imagined curve that assigns an energy cost to every possible value the field could take. Picture a rolling surface with hills and valleys. The horizontal direction stands for how strong the field is. The vertical direction stands for how much energy the universe pays for the field to hold that strength. And just as a ball rolls downhill and settles at the lowest point it can find, the field settles into whatever value sits at the bottom of a valley in this landscape. The shape of that landscape is one of the most important things in all of physics. It decides where the field comes to rest, which sets the properties of empty space itself, which shapes the masses of particles, the strength of forces, and the character of the entire universe we inhabit. Change the shape of the valley, and you change the vacuum, and you change everything built on top of it. Picture a marble dropped into a large curved bowl. It rolls around, loses its wobble, and comes to rest at the very bottom, sitting quietly at the lowest point. The field is that marble. The vacuum we live in is the spot where it has come to rest. And the shape of the bowl, gentle or steep, single-bottomed or riddled with dips, governs where the marble ends up and how it would behave if something ever nudged it. For a long time, the comforting assumption was that our field sits at the true bottom of its landscape, the lowest possible point, a resting place that is permanent and final. The marble has rolled to the deepest part of the bowl, and there it will stay forever. The vacuum we know is the ground floor of reality, with nothing beneath it. But that comfort depends entirely on the full shape of the landscape, including regions we have never been able to explore. We know the shape near the bottom where our field currently rests. We have almost no direct knowledge of what the landscape looks like far away from that point, out in the strange territory the field has never visited. And the whole question of our vacuum's fate hides out there, in the unmapped distance. Because there is a genuinely unsettling possibility, one that follows directly from not knowing the far shape of the landscape. What if the valley our field rests in is not the deepest one? What if it is only a comfortable dip, a ledge, with an even lower valley waiting somewhere beyond a hill we cannot see? If that were true, then the ground beneath all of reality would only be pretending to be solid. Here is the possibility that turns the vacuum from a puzzle into a quiet horror. Our empty space might be resting on a false bottom. Return to the marble in the bowl, but change the shape of the bowl. Instead of a single smooth basin with one lowest point, Imagine a landscape with two valleys separated by a hill. The marble rolls into the first valley it reaches and settles there, sitting still at the bottom of that dip. It looks perfectly at rest. It looks final. But over the next hill lies a second valley, deeper than the first. A lower resting place the marble never found. A marble parked in the shallower valley is in a strange kind of state. It is stable, in the sense that it will sit there quietly, held in place by the walls of its dip. Yet it is not truly at the lowest point available. A deeper valley exists, and the only thing keeping the marble from it is the hill in between. Physicists call this a false bottom, a resting place that feels permanent but secretly is not. And our vacuum, the empty space we live in, might be exactly this. Our field may be resting not at the true lowest point of its landscape, but in a shallower valley, with a deeper one lurking somewhere beyond a hill we cannot see. If so, then the ground floor of reality, the vacuum everything is built upon, is not the true ground floor at all. It is a ledge above a drop. The unsettling truth is that we do not know which case we are in. Discovering the answer means learning the shape of the landscape far from where our field rests, out in that unmapped region, and the tools to probe that distant shape are only now being sharpened. We are, for the first time, beginning to ask whether the floor beneath everything is solid rock or a thin crust over a deeper pit. Picture a house that has stood peacefully for generations, and then someone taps the cellar floor and hears a hollow echo. The house has not moved, nothing has changed. Yet the ground you trusted completely is suddenly a question, a thin shell with an unknown depth below it. That tap is what physicists are now performing on the vacuum of the universe. If our vacuum truly sits in a false bottom, it carries a chilling name. Physicists call it a metastable vacuum, stable enough to have lasted for the entire history of the universe so far, but not truly permanent, a state that could, in principle, someday find its way over or through the hill and tumble down into the deeper valley below. And the ordinary intuition says a marble stuck in a valley can never climb the hill on its own. That intuition comes from the everyday world. In the quantum world, the rules are stranger and far more dangerous. A field trapped in a shallow valley has a way of reaching the deeper one that requires no climbing at all. It can simply appear on the other side of the hill without ever crossing it, and when it does, the consequences would spread across the universe faster than any warning could ever travel. If our vacuum truly rests in a false bottom, then somewhere, someday, it could slip, and the way it would slip is one of the most terrifying scenarios in all of physics. In the quantum world, a field trapped in a shallow valley is not sealed there forever. It has a bizarre escape route. Through the strange rules of quantum behavior, the field can suddenly appear on the far side of the hill without ever climbing over it, a trick that has no equal in the everyday world. It would not happen everywhere at once. It would begin at a single point in one tiny patch of space, where a bubble of the deeper vacuum blinks into existence. Inside that bubble, empty space would rest in the lower valley, the true bottom, with different properties from the space around it, and that bubble would not sit still, because the inside holds less energy than the outside. The bubble would be driven to grow, its wall racing outward, swallowing the old vacuum and converting it into the new one as it went. Here is the part that removes any hope of escape. That bubble wall would expand at nearly the speed of light. Nothing could outrun it. Nothing could even see it coming, because any warning signal travels at the speed of light too, and the wall follows right on its heels. The first moment you could possibly learn that the bubble existed would be the moment it arrived. There would be no alarm, no gathering darkness on the horizon, no time to react. Only a wall of new reality sweeping in at the ultimate speed, rewriting everything it touched. Picture a sheet of glass with a single hairline crack appearing at one edge, and then that crack racing across the entire pane faster than your eye can follow, shattering the whole sheet before you register that it began. Now imagine the glass is not a window but all of space, and the crack does not merely break it but replaces it with something new. That is vacuum decay, a bubble of altered emptiness, expanding at light speed, remaking the universe as it spreads. This is not idle fantasy. It is a genuine prediction that follows directly from the physics of fields and their landscapes, taken seriously by serious physicists. If our vacuum is metastable, resting in a false bottom, then such a bubble can form, and given enough time, eventually will. The only questions are whether our vacuum is truly metastable, and if so, how long the wait might be. And the answer to that second question offers a strange kind of comfort, at least for now. Even in the scenarios where our vacuum is a false bottom, the hill holding us in place is enormous, and the odds of a bubble forming in any reasonable stretch of time are almost unimaginably small. The expected wait would be vastly, absurdly longer than the current age of the universe, so long that there is no practical reason for fear. But comfort is one thing, and the deeper question is another. Because what would that expanding bubble actually do to everything caught inside it? What happens to matter, to atoms, to the very rules of chemistry when the vacuum itself is rewritten? The answer is that the world you know would not survive the crossing. Imagine standing just outside that expanding bubble in the final instant before it reaches you. What waits on the other side of that wall? The honest answer is a reality where the rules that build you no longer hold. When the vacuum shifts from our valley to the deeper one, the resting value of the field changes. And that field is the very thing that hands mass to many of the fundamental particles. Change its resting value, and you change the masses of those particles, perhaps drastically. Some might grow far heavier, others might behave in ways they never could in our universe. Follow that downward through everything built on top of it. The particles that make up atoms depend on their exact masses to hold together in the delicate arrangements we call matter. The forces that bind them depend on the properties of the vacuum they act within. Shift the ground rules, and atoms as we know them may not be able to exist at all. The careful architecture of protons and neutrons, of atoms and molecules, of chemistry and everything chemistry builds, could simply come undone. So inside the bubble, there would be no atoms of the kind that make up your body, no molecules, no chemistry, no structures capable of holding together the way matter holds together here. Whatever exists in that new vacuum would follow different laws and take different forms. Forms with no room in them for stars, planets, or living thing. The bubble would not merely destroy the world, it would replace the very possibility of a world like ours. Picture the entire universe as a sprawling song played on instruments tuned to one precise pitch. Every note, every harmony, every melody depends on that tuning. Now imagine a wave sweeping across the orchestra, retuning every instrument to a completely different pitch as it passes. The song does not just stop, the instruments can no longer play it at all. The bubble is that wave, and matter is the song. This is the ultimate stake hidden inside the physics of empty space. The question of whether our vacuum sits at the true bottom is not an abstract curiosity for specialists. It is a question about whether the ground beneath all of existence is permanent, or whether it is a temporary arrangement that could, in the fullness of time, give way to something in which we could never have existed. And here the vacuum catastrophe, the false bottom, and the deepest fate of the universe all braid together into a single thread. The energy of empty space, the shape of its landscape, the stability of its resting place. These are not separate mysteries. They are different faces of one profound uncertainty about the nature of the nothing that fills all of reality. The pressing question then becomes brutally practical. Which is it? Does our vacuum rest safely at the true bottom, permanent and secure? Or does it perch in a false valley, waiting across unthinkable ages for a bubble that will someday erase everything? Astonishingly, we may already have the clue that answers this. It is hidden in the masses of two particles we have actually measured. And when physicists plug those numbers in, the universe appears to be balanced on a knife's edge. When physicists take the masses of two particles we have actually measured and feed them into the equations, the result is deeply unsettling. Our universe appears to be balanced right on the edge of stability. The shape of the vacuum's landscape, especially in that far region we cannot directly explore, is not fixed by magic. It is pulled and shaped by the particles of nature through the endless way they interact with the mass-giving field in the churning quantum vacuum. Two particles dominate this tug of war. One is the heaviest particle we know, an enormously massive quark. The other is the particle tied most directly to the mass-giving field itself. These two pull the landscape in opposite directions. The heavy quark, through its constant interaction with the field, tends to drag the far side of the landscape downward, threatening to open up a deeper valley out beyond the hill, which would leave our vacuum sitting in a false bottom. The other particle pulls the opposite way, working to keep the landscape rising and our resting place secure as the true bottom. Which influence wins decides whether our vacuum is permanently stable or merely metastable. Now, here is the astonishing part. When physicists plug in the actual masses they have measured for these two particles, the contest comes out almost exactly even. Not a clear victory for stability, not a clear sentence of doom, a near-perfect tie, with our universe balanced right at the boundary between the two fates. The measurements place us in a delicately poised situation, tantalizingly close to the dividing line. The best current readings hint that our vacuum may be metastable, a false bottom after all, but only barely, and with a lifetime so staggeringly long that a bubble forming any time soon is wildly improbable. We appear to be perched on a razor's edge, leaning perhaps a hair toward the unstable side, yet held in place by a hill so vast, the weight for collapse dwarfs the age of the cosmos many times over. Picture a boulder resting at the very lip of a cliff, poised so finely that a feather could seem to decide its fate, yet so heavy and so wedged in place that it has not moved in ages and shows no sign of moving. That is where the measurements seem to place our vacuum, right at the edge, and yet, for now, utterly still. Why the universe should be balanced so precisely at this boundary is a mystery in its own right. It could be a meaningless coincidence. It could be a profound clue, a signal that some deeper principle we have not yet grasped is holding the vacuum right at the tipping point for a reason. Physicists genuinely do not know. The knife's edge is real, and its meaning is wide open, but everything rests on how precisely we know those two masses and how well we understand the shape of the landscape they carve. A small shift in the numbers could tip our verdict from stable to metastable, or back again. To know our true fate, physicists need to measure the vacuum's landscape with far greater precision than ever before. And that is exactly what the largest machines ever built are now straining to do. To learn the true shape of empty space, physicists have built the most powerful machines in human history and aimed them straight at the vacuum. The greatest of these is a vast ring buried beneath the border of two European countries, a tunnel many miles around where particles are driven to nearly the speed of light and smashed together in tremendous collisions. Each collision concentrates so much energy into so small a space that, for the briefest instant, it recreates conditions not seen since the newborn universe, conjuring rare particles into fleeting existence so they can be studied. One of these machines' deepest goals is to probe the mass-giving field directly, and in particular, to measure how that field interacts with itself. This self-interaction is the key. It carries information about the curvature of the vacuum's landscape away from the resting point, out toward the strange far region that decides whether a deeper valley waits beyond the hill. Measure the self-interaction precisely, and you begin to read the shape of the landscape in exactly the place that determines our vacuum's fate. Reaching that measurement is fantastically hard. It requires forcing the field to reveal its self-interaction in events so rare that only a handful appear among trillions upon trillions of collisions. Physicists must sift through mountains of data, hunting for the faint, specific fingerprint of the field acting on its own presence, gathering these precious events one by one over years of patient running. Every event nudges the answer a little closer, sharpening our picture of the landscape's true curvature. Picture cartographers trying to map the far side of a mountain range they can never actually visit, forced to infer the distant peaks and valleys from tiny tremors felt faintly at their feet. Each tremor is almost nothing on its own, but gathered by the thousands and read with care, they slowly reveal the hidden shape of the terrain beyond the ridge. That is what these experiments are doing, mapping the unreachable landscape of the vacuum from the faint tremors of rare collisions. And this is only the beginning. Physicists are already designing even larger machines for the future, rings many times bigger, capable of far greater precision, built in part to pin down these very numbers with the accuracy the question demands. The goal is to measure the shape of empty space precisely enough to finally answer whether our vacuum is truly stable or a false bottom waiting on a bubble. The stakes of these measurements reach far beyond a single number in a table. They touch the origin of the universe, the reason it is filled with matter, the true nature of the dark energy stretching it apart, and the ultimate fate of the vacuum we all live inside. A single, precise reading of the vacuum's landscape could ripple outward into nearly every deep question physics has. So the great flaw that opened this story, the monstrous mismatch between the predicted and the measured energy of empty space, turns out to be woven into all of it. And standing back to take in the whole tangled picture, one realization rises above the rest, larger and more important than any single piece. The flaw is trying to tell us something, and learning to hear it may be the most important task in all of physics. Step back and look at the whole strange journey, and a single truth comes into focus. The great vacuum flaw is not merely an embarrassment to be explained away. It is a signpost, pointing at something enormous that we have not yet understood. Consider where the catastrophe actually comes from. It appears at the exact place where our two greatest theories of reality meet and refuse to agree. On one side stands quantum field theory, our magnificent description of the smallest pieces of the world, the framework that fills empty space with humming energy and predicts it to be monstrous. On the other side stands Einstein's theory of gravity, our magnificent description of space, time, and the cosmos, which insists that all energy must gravitate. Each theory is triumphant in its own domain, and where they overlap, on the question of how the energy of empty space bends the universe, they produce an answer that is catastrophically wrong. That is the deepest clue of all. A contradiction, this violent, at the precise seam between two great theories, almost certainly means that neither theory is the final word. Something deeper is missing, some grander framework that would contain both quantum theory and gravity as pieces of a larger whole, and would explain why the energy of empty space behaves the way it truly does, rather than the way our current mathematics blindly predicts. Physicists have a name for the missing framework they are hunting: a theory of quantum gravity, a single unified description that weds the quantum world of particles to the smooth geometry of space and time. We do not yet have it, but the vacuum catastrophe may be one of the clearest fingerprints it leaves, a place where the absence of that deeper theory shows up as a howling, 120 wide gap in our understanding. Picture two perfectly drawn maps of the same coastline, each flawless on its own, that simply do not line up where their edges meet. The mismatch at the border is not a flaw in either map alone. It is a sign that some larger, truer map exists, one that would make both fit together seamlessly. The vacuum catastrophe is that mismatch at the border of physics, and it points toward a truer map we have not yet drawn. This reframes the entire mystery. The worst prediction in the history of science is worst precisely because it marks the spot where our knowledge runs out most dramatically. It is not a small crack to be patched and forgotten. It is a doorway flung wide open onto physics we have not yet discovered. The very size of the failure is a measure of how much remains to be found, and that is why physicists keep returning to empty space, again and again, with ever more powerful machines and ever more daring ideas. They understand that the humble vacuum, the nothing that fills every corner of reality, holds one of the greatest unsolved secrets in all of nature. So the journey ends where it began, staring into the emptiness in front of your face. Except now, that emptiness looks entirely different. It is no longer a silent void. It is a churning ocean of energy, shaped by a hidden landscape, balanced on a knife's edge, guarding a mystery vast enough to overturn everything we think we know about reality. And the final question left hanging is the one that makes this entire story matter to you, standing here at the edge of the unknown. At the end of all of it, one truth remains, and it changes how you see the world around you. The empty space you move through every second of your life is the deepest mystery in physics. Reach out and wave your hand through the air. Then imagine removing the air and every particle and every ray of light until nothing at all remains. What is left is not a silent void. It is a seething ocean of energy, humming on countless notes, boiling with particles that flicker in and out of existence, shaped by an invisible landscape and carrying within it the fate of the entire universe. Our finest theory says that empty space should weigh enough to have torn the cosmos apart before a single star could form. The real universe carries only a faint whisper of that energy, gentle enough to let galaxies gather and life arise. The gap between the two is the largest error ever recorded in science, a one followed by more zeros than there are atoms in everything you can see. And after decades of the sharpest minds hurling their best ideas at it, that gap still stands, unexplained, at the very center of physics. We have chased it through elegant symmetries that broke, through vast collections of unseeable universes, through the daring claim that the catastrophe was never real, and through the chilling possibility that the ground beneath reality is a false bottom, holding us above a deeper vacuum that could someday sweep across everything at the speed of light. Every path led deeper into mystery rather than out of it. And that is the strange gift hidden in this whole story. The vacuum flaw is a signpost, planted at the exact place where our two greatest theories collide and fail to agree, pointing toward a deeper understanding of reality that no one has yet reached. It marks the frontier of human knowledge, the place where the map runs out and the unknown begins. Picture standing at the shore of an ocean at night, looking out at water so dark and vast you cannot see where it ends. For most of history, people believed empty space was that dark water's opposite, a perfect blank, a pure nothing. Now we know the nothing is the ocean, deep, restless, full of hidden power, stretching far beyond the reach of everything we understand. So the next time you find yourself in a quiet room or looking up at the black spaces between the stars, remember what is truly there, not emptiness, a humming, churning, energy-soaked vacuum holding a secret so large it may one day rewrite our entire picture of the universe. The nothing that fills all of reality turns out to be the thing we understand least, and the thing that matters most. The greatest mystery in physics was never hiding in some distant galaxy or exotic particle. It was here the whole time, in the empty space in front of your face, waiting for us to look closely enough to finally see it.